Okay. It probably posted around 10 anyway. Okay. All right. So let's see. Okay. So which problem?
9.3, number 6. 6 through, well, what is it? 8, basically.
Oh, right. I just got an email about these. Right. Okay. Now, first of all, I need to comment that where do I want to go? I'll go here. All right. So, okay. Oh, just realized the tablet might help. Oh, okay. All right. So if we look at see 9, 3, 6 to 8. Okay. Now, one key thing to remember is that if an infinite geometric series converges, its sum is given by a particular formula. And this is something that I would expect people to remember for like a final, which is that it goes the sum is given by a sub 1 or simply a. It doesn't have to be a sub be called a sub 1, but the initial term over one minus r. Okay, where r is the common ratio. Now, when does such a series converge? Such a series converges if and only if the absolute value of r is less than 1. That's the way most calculus books write it, which means that r is strictly between -1 and +1. Okay, so you have to use that formula. And yeah, so with these, you would refer back to 3, 4, and 5. Okay, so the geometric sequences we talk about here. In 3, I tell you the common ratio is -4. Does -4 satisfy this condition? Does r equals -4 satisfy this condition?
No.
No. Therefore, the series converges or does not converge. The series does not converge. We say it diverges.
Oh, okay.
Okay, so not converges means diverges.
Oh, so it's basically like the same questions as like 3D, 4D, like as n approaches infinity, do the terms of the sequence approach a real number?
Well, no,
Is
that's a bit different. I mean, because D refers to the numbers in the list, right? 6, 7, and 8 deal with the idea of a sum. Well, the series represents an attempt to take a sum, right? So basically, a series, a series goes like this. So summation a sub n equals 1 to infinity. That'll be an attempt to take a sum, and so on and so forth. But the sum, but the thing is, this may have a sum or not. In order for this to actually have a sum, we need the partial sums to approach a real number. So we would need this partial sum, this partial sum, this partial sum. That would have to approach a number if the series converges. If r is -4, you're not going to get a sum.
okay.
Because the partial sums are all whacked out. Because the terms are going to be like, the terms are going to be something like 5, -20, 80. There's no way that these cumulative sums are going to approach anything. All right, so there's no sum.
Okay.
And the series diverges. Well, that's the issue. See, in 3, no, my iPhone's talking. All right, so here we just consider the terms. Actually, the issue of the sum comes up in 6, right? 6 refers to 3. 6 does a series consisting of these terms Does it converge or diverge? And the answer is it diverges. By definition, it has no sum. That's why I say if the series converges, find the sum. If it diverges, then by definition, there is no sum. And by a sum, we mean a real number.
Okay. Okay, and then for number 8,
8 on this one?
yeah.
Right. So you had to find the common ratio.
Yeah,
And-
for 5,
Yeah.
I have a ratio for it. It's where is it? -2/5. How would
Right.
you solve for it though?
How would you find it?
No, how would you solve it? Because it converges because it's the absolute value of that is less than 1.
I mean, how do you find the sum?
Yeah.
Yeah. Okay. So let's see here. All right. So purple's fine. Okay. So let's go to purple. Okay. So on number 8 here, which refers back to 5. Okay. So on 9, this 9-3. Okay. So from 5, we got that R was -2/5, so you found that. Okay. And since you're right, it satisfies the convergence condition. So that means that the series, by definition, only a geometric series has a common ratio R. The series converges. All right. And then how do you find the sum? The sum S is again obtained by the formula that I just mentioned over here. It's the initial term. I don't care if you call it a sub 1 or not, but it's the initial term over 1 minus R. So it's the initial term, A if you wish, over 1 minus R. Okay, A or a sub 1. Okay, the first term matters if you care about the sum. First term is 3 over 1 minus R is -2/5. That sounds familiar. All right. And then it's just a matter of working out the compound fraction. So you have 3 over 1, and that's plus the 2/5. All right. Any questions thus far?
No, I think I'm on the right track for it.
Okay. What's 1? 1 is 5/5. 5/5 plus 2/5 is 7/5. So we have 3 over 7/5.
Yeah, so it's 15/7.
Right. So 3 is 3 over 1. When you divide by a non-zero value, you multiply by its reciprocal, which is 5/7. You're right. It's going to be 15/7. Okay. Or if you wish, 2 and a 7th as a mixed number.
Okay, and then I haven't tried the rest of 9.3, so I'm gonna do that after. But so I just skipped the rest of 9.3 because I didn't do it, and I went on to the rest of them. And then the only other problem that I have a question on is 9.5, number 5.
And by the way, on the rest, so A, write the series using summation notation. So if you can get the general nth term and stick one of these guys in front, that's basically the idea. We just talked about conditions for convergence or divergence and find the sum. So basically, this discussion should help, except with A, just remember that you want to find a form for the general nth term and stick one of these guys in front.
Okay.
Right. Okay. Now you said, was it 9.5?
9.5, number 5, yeah.
Right. Okay. And that's actually a pre-calculus problem. So who knows? It's possible I might grade it. All right. So I'll go to that one now. Well, any of these is possible. Okay. So let's go to blue. Mix things up. All right. So 5, the difference quotient. So I wanted to remind people what this thing is. Remember that when you see this, you're thinking what S word? F of x equals x cubed how do you express f of x plus h? It's that s word. Substitution. Substitution. Okay. All right. So f of x plus h minus f of x all over h. Okay. So we're going to have to simplify this difference quotient. All right. All right. So, okay. Get this fraction bar first. All right. So what is, okay, so what's the deal? So we have f of x equals x cubed. All right. So substitution, the idea is that wherever we see an x, we're going to replace with x plus h. Okay. So we replace x with x plus h here. We also replace x with x plus h here. It's a substitution. So I'll put this in red. I'll go ahead and put this in red. If f of x is x cubed, do you know what we mean by f of x plus h? Do you know what I mean by substituting?
Not really.
It's the cube of, it's not x anymore. It's x plus h. So this is what students need to understand when they do difference quotients in calculus, because you're going to see this in calculus because the limit definition of the derivative is the limit of a difference quotient. So you're going to use this to derive the derivative of x cubed. So once again, if f of x is x cubed, that means that I'll go ahead and write this here. That means that f of x plus h, this is something we mentioned back in chapter 1, is going to be the cube of x plus h. Two ways to look at this. What does the function do to its input? Here, the function cubes its input. That's easily stated. It's not always easily stated if you have a big old polynomial, but like with 5 terms or something. But here, it's easy to say that f cubes its input to get the output. Here, again, what does f do? It cubes its input in order to get the output. So here, you're cubing x. Here, you're cubing x plus h. Another way to look at it is a substitution. Okay, every time you see an x here, you substitute it with the quantity x plus h. Okay, so that's the big part of it. If f of x is x cubed, f of x plus h is the cube of x plus h. Okay, any questions about that? It's a substitution. X plus h goes here, x plus h goes here.
Okay, I got that.
You got that? Okay. I'll do the rest in blue. But yeah, that's the big hurdle. Well, once students get that, then that's the big hurdle for a lot of people, but there's still more.
Yeah, I just totally forgot that rule.
Right. Okay, evaluating a function. It's a substitution. Whenever you evaluate a function, it's a substitution. For example, let me do a simple example. Do some purple. If I asked you what f of 2 was, if f of x is x cubed, what's f of 2?
2 cubed.
Right. What'd you do?
Just plug 2 in for x.
Yeah, it's the same idea. Except here, instead of plugging in x, you're plugging in this weird guy, x plus h. But it's the same idea, right? I mean, if you agree f of 2 is 2 cubed, you agree that f of x plus h is x plus h all cubed, right? It's the same principle, just an uglier thing you're cubing.
That's yeah, okay.
Yeah. That's why, sometimes it's easier to think of the basic case. That was true way back in factoring, right? Sometimes it's easier to think, what if I plugged in a number, right? Well, you substitute. Okay, I'm going to go back to blue. Minus f of x is x cubed. Okay, I gave you that all over h. Okay. Now, why is this in 9.5? Because when you cube this thing, that's going to involve the binomial theorem. Okay, that's going to need the binomial theorem. Okay, and are you familiar with how to apply the binomial theorem?
Yeah, isn't it the pyramid thing? I forgot what it's called.
Pascal's triangle.
Yeah.
Yeah.
Pascal's triangle. Yeah.
Pascal's triangle, right? That helps.
I always
with
forget the name of it, but yeah, I know how to do it. I just forgot what it was called.
Yeah. Pascal's triangle gives you the coefficients, and then you do the whole, powers of x, powers of h. Okay.
Mm-hmm.
So basically, you get a big old polynomial in x and h, right? Let me you get a big old polynomial minus x cubed. It turns out you start off with an x cubed, so you get a cancellation. All over h. And it turns out h will be a factor of this junk in here, right? Because the h blends into a lot of these terms here. And then you'll be able to factor the h cancel. And your answer will ultimately be this guy in here.
Okay. I think I can solve the rest now that I got that first piece.
Right.
And I think that's all for me. Unless if you have more time, I for 9.4 the mathematical induction
Right.
for number 1,
Mhm.
I really didn't know what I was doing. I was kind of just copying what the guy on the Khan Academy video did. I watched it like twice and I still didn't really understand it fully. I just don't really understand how like they got that answer from that.
Oh, okay. Now, first of all, this is okay. In terms of how we get the formula, that's kind of a guess based on like the handshake problem. We kind of conjecture at or guess at what the formula is. Induction doesn't tell you how to come up with the formula. What you need to do is, as a mathematician, what you need to do is you need to guess at the formula, and then the hope is that it's the correct formula, and you can prove this conjecture by using induction. So induction is not a way to come up with a formula from scratch. You get the formula from observing patterns, like that, like from the handshake problem. But here I'm presenting to you a conjecture, a guess, and then it turns out that it's true, and you can prove it by using mathematical induction. So induction does not tell you how to come up with a formula. It shows how, if you get the right formula for this, it's a way of proving that this works for all positive integers n.
Okay.
So yeah, I can see how that, and then we explained how to get this formula in my video about the handshake problem, because this is the number of handshakes among n+1 people, basically, if everyone shakes each other's hands. Now, that can be done as n+1 choose 2. That can be done as this, as edges and diagonals and an n+1 gone. So there are various ways of looking at this, but you end up with that formula. Now, in terms of the method, well, now, so was that your question? How you get this formula?
Well, the thing is like he proved that formula and said that formula was equal to k+1 times k+1 plus 1 over 2.
Yeah, that
And
part's
then,
confusing.
but
Yeah.
when you plug a value into both equations, you get different values. So I didn't understand it really.
Yeah, it's a different statement for different values of n, right? So let's see. Now I wanted to go to go to a copy of my notes, or maybe I can just do it from scratch, because my notes get wordy. Okay. Okay, so maybe I should have done what Khan did, which is at least do some basic cases. So what does P sub 1 say? P sub 1 says this collapses to 1. So that's the case n equals 1. Okay, what is the statement corresponding to n equals 1? That's the proposition P sub 1, which says if n is 1, that left side collapses to 1. All right, equals, plug in 1 on the right side, you have 1 plus 1 all over 2. Bottom line, that right side is 1. You don't have to show that in great detail.
Yeah.
1 equals 1, which is a true statement. So this formula works in the case where n equals 1. In the case n equals 2, what are we saying? What does P sub 2 say? That
it equals 3.
That 1 plus 1 plus 2 equals, you plug in 2 on the right side, 2 times 2 plus 1 all over 2. Then you get 3 equals 3, and that checks out also. All right.
Oh.
Okay, and then I'll do another one. P sub 3 says 1 plus 2
Okay.
plus 3 is
I
plug in
see.
3 for n.
I see what it is now. For the left side of the like when where it says like n equals 2, I was just doing 2. I wasn't accounting for 1 plus 2, which is why I was getting like different answers on both sides, which is why I was really confused. So I don't know why I wasn't doing like 1 plus 2 and then 1 plus 2 plus 3 for like P3.
Well, yeah, it's a
I
matter
was
of
just
students.
doing 3, and then I was like, why the heck is the other side
Oh
not
yeah,
3?
yeah. It's a matter of students getting used to the ellipsis, which is
Yeah.
some of the first n terms. And one thing to recognize is that if n is small, then like an accordion you're squeezing in or a spring, this left side collapses. So if n equals 1, you don't even have any of this junk. It's just 1, right?
Yeah. Okay, that makes sense.
Right.
I totally missed that.
Yeah, that's why it's
So now
confusing
I
when
get
when you
it.
think about the fairly basic cases here, the first few values of n. Then you have to remember that this thing collapses, which is not implied by the way it's written. That's why the whole thing about the ellipsis, right, is getting students to think in terms of. See, that's why we don't like this form. It's a non-closed form, right? Obviously, as a student, you prefer this, right? But then,
Yeah.
I showed you some clever ways of getting the formula. And then induction is a means of proof where you can prove this formula. And then if I ask you, like on the homework, I basically asked you in problem 2, what's the sum of the first 1,000 positive integers? Okay. Now in this form, it's like, well, forget you, teacher. That's going to take way too long, right? Even with a calculator, 1 plus 2 plus 3 all the way to 1,000. Whereas here, plug in n equals 1,000, no problem. You can do it with a calculator, or if you're sharp on a given day, if my arithmetic's good, then maybe do it mentally, but certainly with a basic calculator, you can plug in n equals 1,000 and work that out very quickly.
Okay, that's understandable now that I caught that.
So that's the purpose. So the idea is that you yourself, through your own cleverness, by looking at basic patterns, like in the handshake problem, you have to come up with what this formula looks like, right? And that's part of the challenge. That's a big part of the challenge. And then to prove it, to verify that, yes, it works for n equals 1,000, n equals 1,000,000, n equals 1,000,000,000, right? You don't have time to go that far, right? So what you do is you can prove by induction to prove that your formula works for, in this case, all positive integer values of n, which you couldn't do brute force. You don't live infinitely long, right? So yeah, it's a method of proof, which you do see in linear algebra. So where do you see this in linear algebra? Prove this statement for matrices of size, square matrices of size 1 by 1, 2 by 2, 3 by 3, 4 by 4. I remember when I taught linear algebra a long time ago, 254. We had proofs by induction, and very few students knew what that was. So, for example, you can prove a property for all square matrices, or a property for all determinants of square matrices: 1 by 1, 2 by 2, 3 by 3, 4 by 4. So, proof by induction was something we saw in linear algebra. Matrices.
Yeah. Okay.
But then go back to your point, and in fact, I've seen mathematicians write this in books. You might go, so how do they come up with their formulas? Well, crank through a bunch of 1 by 1 matrices, 2 by 2 matrices, maybe 3 by 3 matrices by hand or with a computer, right? Work out their determinants maybe, and see if you get a pattern. And then you might figure out, this determinant thingy, this formula of a determinant is given by n cubed plus n or something like that, right? Where you have an n by n matrix. But then you come up with this by just using some basic matrices with numbers 1, 2, 3, 4, right? And just play with matrices. I've seen mathematicians write that in books. If you want to come up with theorems with matrices, start with small matrices and plug in numbers and compute like crazy. So it all comes down to the basics.
That sounds difficult.
Well, yeah, that's what professional mathematicians do. Yeah.
All right. Well, I think that's all for me. I only have to do those few problems from 9.3 and then the polar coordinates, and then I'm done.
All right. So now, if you want, I can stay. I can stay in this room until 7:45. Well, in the meantime, I have some work to do. But would you like me to come back and check on you? Why don't you email me if you have an issue? I'll check my email. I can be here until 7:45. So if you have an issue, I'll keep checking my Yahoo email. All right. So if you have a question, I'll check my Yahoo email.
Okay, awesome. Thank you, Professor.
Okay, you're welcome. All right, good luck.
Thank you and bye.